Section 8.3 is finding volumes of solids with known cross sections. You might be asking what the heck those are, but we'll get that here in just a second. So in geometry, right, we found volumes of all kinds of three-dimensional shapes, cubes, spheres, cones, rectangular prisms, and maybe even others. What we're going to do, or what calculus allows us to do, is to find the volumes of solids whose bases are two-dimensional regions on the xy coordinate system, and then their heights are cross-sections that come up from the graph. They're kind of like they're sticking out from the base. Those cross-sections can be different shapes, so sometimes they might be semicircles or squares or triangles. But it's a third dimensional, right? We're talking about three-dimensional now. Let me kind of show you what that looks like. So let me pull this up here. So here's an example. So if you see that purple region in there, let me actually turn this off for a second. So you see that region right there. That is the region that's going to be the base of our cross sections. All right, and then we can choose our cross sections. So let's start with a square. And then we're going to see what happens as I drag this across. You'll see those squares are coming out of the base. Go all the way across. And what that's going to do is form this three-dimensional shape. Now, I used 51 squares, right? As I make that, if I use more and more squares, you can see how it gets smoother and smoother. So what we're doing in calculus is we're making the widths of those squares infinitely small, okay, as we go across there. So that's the example with squares coming out of the bottom. Let me show you with equilateral triangles. So this is a little hard to see. Let me rotate the shape a little bit. Oops, that was a little too far. But you can see how those are just triangles. Let me actually drag this across. This may be the best way to show you. So as I come across, you'll see those triangles. And let's turn down these so you can see it a little bit better. So as I go across here, you'll see those triangles like popping up out of there. So instead of squares, now I have those triangle cross sections that are coming out at you. You can change it to semicircles. So you can see how that shape looked like there. So there's three examples of what these cross sections might look like. So hopefully that gives you like a visual representation. So we have this region that's on the XY coordinate plane, which in this picture is the red and the green axis. And then you have these cross sections that are coming up out of that region. And those cross sections, they can be different, and finding the volume will be different depending on what the cross sections are. Here's some more pictures of what it might look like. So here's a region, and those are some semicircle cross sections coming out. There's some, looks like rectangles. There's some squares coming up out of the graph. There's some with watermelon. Cute, right? This is one where you have this region, looks like a parabola. And then you have square cross sections coming out. Here's another one with square cross sections. So you can kind of picture what that looks like. Now, again, when we do it in calculus, what we're doing is we're making those cross sections infinitely thin. And so it won't look like individual squares. It'll actually it will become smooth, kind of like you can see those individual semicircles. But in calculus, we're making those semicircles infinitely, the width of them infinitely small. There's 100 of them, but we're going to do more than that. And it pretty much just ends up looking like a smooth figure. Okay, so let's talk about how we'd find the volume of those. This is going back to your book. Before we get into finding the volume of those shapes that are formed, make sure you're familiar with these common area problems. Right, the area of a square, you just take one side and square it. Rectangle is base times height. Semicircle is 1/2 pi r squared. Right, pi r squared is a circle, so 1/2 pi r squared is a semicircle. A triangle is 1/2 the base times the height. I think we're pretty familiar with those. Equilateral triangles is probably something that we're not familiar with. That's just going to be something you're going to memorize. If it's an equilateral triangle, you can actually just find one side, right? All three sides are equal. You can find one side and plug it into that formula. So square root of 3/4 times the side squared. So keep those, again, I think the first four, there's no need to memorize those. Equilateral triangle, there probably is. We probably you've never seen that before. Okay, So when you want to find volumes of solids with known cross sections, these cross sections that come out of them, okay, here's how we're going to do it. The first thing is you have to be careful with the wording. So some of them will say perpendicular to the x-axis, some of them will say perpendicular to the y-axis. So if it's perpendicular to the x-axis, what I do is I find A, which represents the area of the cross section. And the area of the cross section has to be in terms of x. So I come up with an expression that represents the area of the cross section in terms of x. That's what I'm going to plug in right there. And when you integrate it, you're integrating it with a dx. Also, your limits also have to be in terms of x, so going from left to right. If it's perpendicular to the y-axis, then same thing, we still come up with an area formula, but this time our area formula is in terms of y. It's a function of y. And our limits are also in terms of y. So instead of going left to right, you're going to say, what's my lower limit? What's my upper limit? You're going up and down that direction. These will make more sense, I think, once we go through and do an example here. So let's do this first example. It says, find the volume of the solid whose base is a triangle bounded by the line y equals negative 2x plus 2, x equals 0, and y equals 0, and whose cross sections are squares which are perpendicular to the x-axis. So they already have the graph drawn for us over here. This is my region over here, right? This is the line y equals negative 2x plus 2, x equals 0 is that vertical one, y equals 0 is that horizontal one. So we have that area formed. Okay, the two things you have to be really careful with is there's two things you have to identify. First of all, what kind of cross sections are you doing? So in this case, the cross sections are squares. And then what is it perpendicular to? So it's perpendicular to the x-axis. I would always start by drawing a cross section. So what we're picturing here, right, is that my cross section is perpendicular to the x-axis. So this is a cross section, it's a representative cross section. In reality, you're going to have an infinite amount of those cross sections. This one's just going to represent all of them. So up out of that blue line, you can picture a square coming up out of it. Okay, so what we're going to do, right, we always start out with our volume formula. The volume is, because it's perpendicular to the x, it's the area formula times dx. Okay, now I just plug in what is the area formula, where the area formula for a square is the side squared. And now I have to come up with, how do I represent s? I want it to be in terms of x. So how do I represent s in terms of x? Well, if you picture that square coming up, this blue line right here is one side of those squares. So if I could come up with some way to represent that line, right, I could just plug that in for s and square it, and I'd have the area of the square. Well, whenever you have a cross section between two functions, you can always just take the top function minus the bottom function. So what we're going to do, to find the length of that side of the square, I'm going to take the top section, which is negative 2x plus 2, minus the bottom section, which is 0. So that would give me one side length. So s comes out to be equal to negative 2x plus 2. That's how long that segment is. So now I come up over here, I take what I got there, and I'm going to plug it in for s over here. So I have the integral from, by the way, the 0 to 1 is because I'm going from when x is 0 to when x is 1. It's between those two x values. And they're x values because we're doing it in terms of x. It's a dx. Okay, so we're going to take that negative 2x plus 2 and plug it in for s. It's negative 2x plus 2 squared dx. And that should be the integral that would allow us to find the area. I'm not actually going to go through and integrate that just for the sake of time. I just want to make sure that we know how to do the setup, right? We ought to be able to solve that if we want to. Okay, so that's one example. Let's do another one that's not squares, and we'll also do one that's perpendicular to the y-axis so you can see that. So if you go on to example 2, it says set up but do not integrate the integrals for the volumes of the solids with the same base as example 1, but whose cross sections are. So these are two different problems. The first one says semicircles perpendicular to the x-axis. And then the second one we're going to do is rectangles of a height 1/4, which are perpendicular to the y-axis. So let's start with A. So ignore B for just a second. Notice we're using the same area we did before. So two things we're going to recognize is, first of all, what's my cross-section shape? And that's, whoops, those are semicircles. And the second thing is, what is it perpendicular to? And that's the x-axis. So come up to my shape, draw the cross-section going across here. So that cross-section is going to look like that. And you're just picturing a semicircle coming up out of there. Okay, so set up our integral. It's going to be the integral from a to b of, we take the area times this dx because it's perpendicular to the x-axis. So that's going to be the integral from, just look at your, it's in terms of x. So I'm going from when x is 1 to, sorry, from when x is 0 to when x is 1. My area formula, I'm doing semicircles. So the formula for a semicircle is 1/2 pi r squared, and it's going to be dx. Okay, we can move the 1/2 and the pi out. So I'm going to come up over here. I have 1/2 pi times the integral of the radius squared dx. Now the last thing is, I don't want an r in there. I want it to be in terms of x. So I have to represent r. So this is a little bit tricky. So if you're picturing a semicircle coming up out from here to here, that's coming up, I need to find out what the radius is. Well, the radius of the semicircle is, if I found the point in the middle, it's that length right there. Or we can go from there down to there, right? It's one of those two lengths from the center of my semicircle. So what I'm going to do is I'm going to find the length, like how long is this? How long is that? Well, we already knew that, right? I go the top, negative 2x plus 2, minus the bottom, which is 0. So that's the length of the whole thing, negative 2x plus 2 divided by minus 0. That would be the diameter of the circle. Well, if I want to find the radius, I would divide that by 2. So negative 2x plus 2 divided by 2, which comes out to be negative x plus 1. That's how long, I'm using lots of different colors here, but that's how long that radius is right there. And you're picturing that radius just rotating around as you form that semicircle. So negative x plus 1. So I come up here. That's all I have really left to plug in. I forgot my 0 and 1 up here. So it's 1/2 pi times the integral from 0 to 1 of, and the radius is negative x plus 1 squared dx. And that integral right there should give me the, will give me the volume of that function that we have right there. Okay, let's try that second one. So the second one's changing, right? So it says rectangles of a height 1/4, which are perpendicular to the y-axis. So I'm gonna erase this up here. I'm actually going to erase example A too, so I have plenty of room to work. So key things, make sure you know what your cross-section is. On this one, it's rectangles. And it's perpendicular to the y-axis. So this is different. So now my cross-section has to be perpendicular to the y-axis, so it's going that direction. What that means is when I go to find my area problem here, it has to be in terms of y. It has to be a dy. That also means my limits are going to be in terms of y. So I'm going from there to there on the y-axis. So my limits are going to be 0 to 2 of dy. And the area formula I'm going to use, in this case it's a rectangle. Well, rectangle is base times height. So base times height. So I just have to come up with something in terms of y that I can plug into there for that base and height. Then I'll have my integral I can find there. Well, if you're picturing that rectangle, the base is right there. That cross section is the base. So we said when you're finding the length of a segment, if it's perpendicular to the x, you go the upper one minus the lower one. If you're finding how long this section is, we go from right minus left. But the tricky thing is here is it has to be in terms of y. This equation is in terms of x. So let's go ahead and switch that around. If y equals negative 2x plus 2, let's solve for x so that it's in terms of y. So I'm going to minus the 2 over. So y minus 2 equals a negative 2x. Then I'm going to divide by negative 2. So I end up with x equals a negative 1/2 y plus 1. That is how long this section, oh, and then I have to go, right, this section. I take the right side, which is a negative 1/2 y plus 1, minus the left side, which is 0. So that length comes out to be a negative 1/2 y plus 1. that's the base of my rectangle. So I'm going to plug that in for b right here. So I have the integral from 0 to 2 of negative 1/2 y plus 1. Just fix that, sorry. Negative 1/2, well, that wasn't any better. Let me try one more time. So my base is negative 1/2 y plus 1. And we have to times that by the height. So if I come back up here, like, what does it tell me about the height? Well, it says my rectangles have a height of 1/4. So they have that constant height. So that's the height. Okay, and that's the integral. That integral is all set up there. If I integrate that, that will tell me the volume of that shape. Again, rectangles coming up out of the top of that. Okay, let's try this next example. So this one says set up but do not integrate an integral for the volume of a solid whose base is bounded by y equals negative x squared plus 2 and y equals x, and whose cross sections are squares perpendicular to the x-axis. So first of all, this does not show me, it doesn't have the graph already done for me, so I'll have to do that. But make sure you identify what are my cross sections. They're squares. What's it perpendicular to? The x-axis. And then let's draw the graph over here. So y equals negative x squared plus 2, it's a parabola, right, moved up 2 and it's opening down. So I don't know, something like, that wasn't very good, but we'll pretend like it was. And then the line y equals x. So y equals x is like this, like diagonal line going up that way. So here is this is my area up here. Right, this is my, I'm just going to erase everything else. Whoops, not too far there. So that's my area right here, this enclosed space inside of there. Okay, we want it to be perpendicular to the x-axis, so my cross-section is going this way. Let me do it a different color. My cross-section is moving this way, and it's a square. So let's go ahead and set it up. I'm going to do the integral from, I don't know what my limits are yet. We'll just leave it a and b because I don't know yet, of the area, and it's dx. And my area formula is going to be the side squared. So I got to figure out how one side of my square is. Well, that cross-section is one side of the square, so I take the top one minus the bottom one. So the length of that segment right there comes out to be the top one, which is negative x squared plus 2, minus the bottom one, which is x. So that is what s is equal to. So the integral from a to b of negative x squared plus 2 minus x dx. Now, the next thing is I got to figure out really all I got left. Oh, I'm sorry, and that's squared, right? That's what s was equal to. So that is, I got to plug it in here, so it's that squared. The only thing I have left now is I've just got to figure out what my limits are. So remember, the way we do our limits is I got to figure out when the two graphs are equal to each other. So take the two equations and set them equal to each other. And remember, you have to include this as part of your work. So you need to show that. So let's move everything to one side. So I get 0 equals, I'm going to add the x squared over plus x minus 2. Factor that. We're going to have plus 2 and minus 1. So negative 2 and positive 1. And that looks like it could definitely fit with my graph. I didn't do the greatest job, but that's your negative 2 right there. That's your positive 1. Sorry, your negative 2 over here. Right, we're looking at the x, not the y. Sorry about that. That's your negative 2, and then the 1's over there is where that one crosses. Okay, so fill those in, and I have my answer. So we're doing the integral from negative 2 to positive 1 of that. This, if I integrate that and solve it, that will give me the volume of that figure. Okay, let's do this last example. So if you're looking at it, it says set up an integral for whose volume of the solids is a semicircle. Whose base is the circle x squared plus y squared equals 1, and whose cross sections are. So we're doing two different problems. The first one is an equilateral triangle. So again, circle that, perpendicular to the y-axis. And it's got our shape over here. So this first one, right, we want our cross sections to be perpendicular to the y-axis. So this is a little bit tricky because there's only one equation. But if we go through and solve for y squared, that will give, I got to solve for either x or y. And that will give me actually two equations. When I take the square root, I'll end up with a plus or a minus. So since we want it is perpendicular to the y-axis, we want our integral to be in terms of y. So I'm going to go a to b of the area dy. That means, if you look up at your equation again, because it just has the x squared plus y squared equals 1, it has one equation. I want my equation in terms of y. So I want to solve for x. So I'm going to take the x squared plus y squared equals 1 and solve for y, or solve for x, excuse me. So minus the y squared over. So x squared equals 1 minus y squared. Take the square root. When I do, I end up with plus or minus the square root of 1 minus y squared. So I actually have two different equations. I have x equals the square root of 1 minus y squared, and x equals the negative square root of 1 minus y squared. So if I come up to here, what that means is the positive is the right side of my circle. This is a positive x equals the square root of 1 minus y squared. The left side, I'll do a different color, the left side over here is just the y equals a negative square root of 1 minus y squared. Okay, so I want to, and as I go across here, I want my area to be equilateral triangles. That's the shape that's coming out of that, off that base. So this is one side of my equilateral triangle right there. And we know that all three sides are equal. So we're just going to plug that in our formula. So make sure you have the formula there for equilateral triangles. We're going to plug that in here. So we got to figure out how long that piece is. Well, to figure out that piece, all I'm going to do is take the right side minus the left side and subtract them. So that's equal to the square root of 1 minus y squared minus the left side, which is a negative square root of 1 minus y squared. Well, that changes to a plus. So that the length of that piece ends up being 2 square root of 1 minus y squared. That's how far it is all the way across. So that's one side of my equilateral triangle. So picture that's one side, and then it's coming up at you out of that shape. So if I plug that in there, right, our formula, look up there for the formula. This is one a lot of us don't remember. But we're going to take square root of 3 over 4. I'm going to move it out in front, times the integral of, and by the way, that one's going from negative 1 to 1, of 2 times the square root of 1 minus y squared squared. Okay. So if I kind of skipped a step there, but what I did was the area formula, right, for an equilateral triangle is square root of 3 over 4 times the side squared. So I moved the square root of 3 over 4 out in front, and then I figured out what the side was. That was the length of this piece right here. So I went the right side minus the left side and ended up with that for the length. I plug that in for the side, and I end up with this. This is the definite integral that I would solve in order to find the volume of that shape that is formed. Okay, let's try part B. I'm going to erase this just so we can see it, so we have more room to work. Okay, so it says this time we're taking our rectangles whose height are 3 times their base and whose base is perpendicular to the y-axis. So again, the key thing here is what's the shape we're doing? Rectangles. What's it perpendicular to? We're still perpendicular to the y-axis, which is nice. That means I can still use these same equations. If it were perpendicular to the x-axis, I'd have to come back up here and I'd have to solve for y to put the equation in terms of x. Okay, so let's see if we can figure this out. So again, I'm doing the definite integral from negative 1 to 1 of, and we're going to plug in of the area, it's dy. Okay, my area, the area is a rectangle, so that's base times height. So I got to figure out some way to represent the base and the height. So what does it say here? It says whose heights are 3 times their bases. So this, and again I'll use a different color, but this is the base of my rectangle, and the rectangle is coming up at you, and the height is 3 times that. So we'd say the base is equal to this, So I now have the definite integral from -1 to 1 of the base, which is 2 square root of 1 minus y squared, times by, and what does it tell us about our height? Our height is 3 times the base. Well, if this is the base, then our height is just 3 times that. Okay. And then I have a dy out there on the end. Okay, so that's our answer. Now, if you wanted to, we could simplify that a bit. You can leave it like that. Whoops, let me get that out of the way there. You're fine with leaving it like that, but if you wanted to, we could simplify it a little bit. We could times the 2 and the 3 together. That'd be 6. You times the square root of 1 minus y squared together. And actually, if you wanted to, you could even, I'm going to stop there, but if you went even further, the square root cancels out. So you could have 6 times 1 minus y squared dy and integrate that. So, okay, but the idea here is this, is always, draw your figure always. Make sure you're careful with what it's perpendicular to, and draw that cross section. That helps a lot. And then you're going to always start out, right? It's always going to be the area with either a dy, dx, depending on what it's perpendicular to. Write down what your formula is for your particular shape. This was a rectangle, so I did base times height. And then you got to find some way to represent your base and your height, or if it's a square, your side. You have to find out some kind of represent it either with x's or y's. And that's where you're going to come up here and find that cross section. In this case, I went right minus left. If it were vertical, then you'd go top minus bottom to figure out that length. Anyway, try a few of these. Let me know if you have questions. Good luck on the assignment.